Hello, my name is Atosh, and today I'll be talking about the physics of hydraulic fracking. Now, we all have a general idea of how hydraulic fracking works. We all picture a pipe going deep into the earth, firing these pore fluids into the rock, and as the pressure decreases, the fluids in the rock flow upwards, and this is how we get natural gas and oil. But what exactly are the stress relations that go behind this entire process? I will start by first looking at this piece of rock. Now imagine that the cylinder is a rock. Usually in the earth, it is experiencing three main stress forces, sigma 1, sigma 2, and sigma 3. Now these three stress orientations can be resolved into two main stress orientations, which is sigma s, which is the shear stress, and sigma n, which is the normal stress, which is normal to the rock surface. Now the stress relations for this rock can be shown in a diagram that is called the Moore stress diagram, which basically looks something like this, where we have sigma n on the x-axis and sigma s on the y-axis. These two lines are equations that look something like sigma s equals mu naught sigma n plus c naught. Here mu naught is the coefficient of static friction, and c naught is the inherent strength of a rock. Now the strength of a rock can be characterized by sigma s, which is the shear strain. So as you can see, when sigma n is 0, there is still some amount of shear strain in the rock which holds it together. Now on this diagram, sigma 1 can be resolved here, or sigma 3 can be resolved here, and sigma 1 can be resolved here. And usually in the Moore stress diagram, it is shown as a circle. Now these lines that we see here, these represent areas of failure, which is areas where new fractures will form. Now if this circle intersects with one of these lines, that's when a failure will occur. The two important quantities that we'll be looking at are this one, which is sigma mean stress, and sigma s max, which is the maximum sigma stress. And this can be resolved into equations that look something like this. I will not be deriving these equations because that would take a long time. This is sigma mean, which is equal to sigma 1 plus sigma 3 over 2. It's just the average. If in this system we introduce a pore fluid, then fluids behave differently than rocks in stress conditions. So if you look at this kind of schematic where we have these rock particles and the rest of it is basically fluids, if you exert sigma 1 here and sigma 3 here, fluids tend to exert a force outward like that. And we're going to call this force the pore fluid pressure, denoted by PF. So now based on this, our new sigma 1, I'm going to call it sigma 1 prime, equals the sigma 1 coming in minus PF. And the same applies for new sigma 3, which is sigma 3 minus PF. This is because inside the rock, there is fluids which will be pushing outward against the sigmas that are going inward. Well, so why is this important? Now if we put these equations into these two relations that we came up with before, we will get something. So for sigma s prime, we're going to get sigma 1 minus sigma 3 over 2. This is sigma s max. And sigma mean now becomes sigma 1 plus sigma 3 over 2 minus PF. Now this minus PF is important because now if we bring this equation into the Moore stress diagram, we see that sigma m moves to the left by the amount of PF. So now if our center of the circle is here and we have the same values for sigma 1 and sigma 3, it's the same difference, which is differential stress, we're going to find that for the same stress circle, it's going to intersect this Moore Coulomb fracture zone. And this is when frictional sliding occurs. When frictional sliding occurs, the pressure drastically decreases, and this is the basis for hydraulic fracking. When the pressure decreases, fluids from these rocks are going to flow upwards, and there's a reduced stress overall. And just in a quick note, this is how also earthquakes can occur due to poor fluids, because they make these new fractures in existing rocks, which can then slide in the future along normal faults. And this is a main concern with hydraulic fracking these days. So thank you for listening.